Okay, hey everyone. We're going to give this a try. I'm going to see if I can do a video lecture along with my PowerPoint and see how this goes. Give this a try this week. And so today we're going to talk about room modes and for acoustic standing wave resonances in a room. Now we've all experienced this already. We played earlier in the semester that was a 50-something hertz tone. We walked around the room and you're able to hear places where it's really loud or an anti-node, or places where it almost completely disappears, which is a node. And those are you experiencing what happens with just one frequency is developing standing waves, and you're hearing the nodes and the antinodes as you walk around and move to different places in a room. So we're going to look at that idea in a little bit more depth and how complex that actually gets, and then how we can actually do some calculations and measurements of that today. So first, actually, we're going to do a little bit of review. And we've talked about standing waves in tubes, and we spent a good deal of time talking about standing wave in a tube in terms of the quarter wave pipe and the Bose wave radio, and the standing waves and instruments and what that means. And then also in the standing waves on strings, we started very early in the semester there. Actually, what did we do? We watched this guy's video, just remember the standing wave on a string.
There we go. That's
the boundary conditions that were created by the endpoint.
6 times the fundamental frequency, which we measured in the beginning.
There were lots of interesting things there that we saw with this video. And then we haven't looked at this yet, but you can look at a very similar kind of thing with what's called a Rubens tube. And if you fill up tube with the gas and light it on fire, of course, and then set it up to an oscillator, you can see the standing waves that develop in the tube. So you've got an oscillator hooked up there, and as he finds a resonance that develops, hey, there it is. There's one. You can see the nodes and the antinodes as the scrolling down to where you can see different frequencies.
272.
And he's actually calling out specific frequencies now. He's got a measurement mark here, so you can actually measure the wavelengths. So that's actually pretty interesting.
292.
You can go back and watch this. There's actually several interesting ones in this. Take that to another level. There's these guys, cymatics, that have done all sorts of really cool visual, musical songs and videos that do all sorts of interesting things like this.
It looks like a graphic equalizer, just made out of fire, which is really visually exciting. It looks like a gothic organ or something like that. So a lot of the testing with the Rubens tube had to do with finding out what waveforms form the most pleasant looking standing waves, and then how we could use that to create a piece of music. To complicate things, I wanted to shoot in slow motion, which meant that...
That's pretty cool. But another thing I hadn't seen until recently was this fire table where he did it in 2 dimensions. So instead of just having a tube, he's got a square with 2,500 holes. He's going to try to find, there, he found a standing wave of a certain frequency.
Here? It's pretty much like the standing wave on the Rubens tube. It's just in this direction. And it's the lowest frequency that makes a standing wave in this box. So this is like the fundamental. It's the fundamental. Can you show me what happens when you vary the volume a little bit?
Awesome, eh? And then let's watch some music here for a second. There we go. So that's pretty cool. And then there's this other idea of a standing wave in 2 dimensions called a Chladni plate. And I'll just play a few minutes of this so you can get an idea. Same idea.
As the speaker vibrates the plate,
The vibrating plate should vibrate the particles of sand.
You see the standing waves
The
that
sand
develop
moves
on
around,
the plate.
but not much.
And where this,
Let's see what happens
so he hasn't
when
found
we
a resonant
raise the
frequency
pitch.
yet. You find a resonant frequency where a standing wave develops, and you get
Look at how the pattern corresponds to this
salt
particular
standing
frequency,
where there's a node,
343
and
hertz.
no salt where
Watch
there's
how
an
that pattern is
antinode.
destroyed as the frequency goes up. And a new
Find
pattern
a
is formed.
find a harmonic or another standing wave. Pretty cool. So back to this. Then a room takes and basically makes all that way more complicated because we're dealing in 3 dimensions, not 1 or 2 dimensions, but 3 dimensions. So let's review a few things real quick. We've talked about sound in free field a few times, and that's this idea of sound when we talk about a point source, right? Where sound basically emanates out of a point source spherically in 3 dimensions. It's said to be in 3D. There's no real true way that that can happen. It's an idealized situation. The only 2 ways that we can kind of actually make it happen is if we say we suspended a speaker way, way, way up in the air where it couldn't even interact with the ground or anything else. Or if we're in an anechoic chamber. An anechoic chamber basically idealizes free field because there's no reflections or reverberations happening because it absorbs all sound. So then when we're in free field, we talk about this inverse square law that we've mentioned a few times, where basically every time we double the distance, whatever that distance is, we double it, we're going to be 6 decibels down. So say we measured out, we were having class today, we would set up a speaker, we'd stand 7 feet back, and we'd measure with an SPL meter what sound was coming out of the speaker. If we walked back to 14 feet, it would be 6 decibels down. If we started at 15 feet and we'd measure it and we'd go back 30 feet, it would be 6 decibels down. If we started, whatever that distance is, you double it, you go down 6 decibels. And why is that the case? That's the case because of the inverse square law, like we said. And here's what that looks like mathematically. Hold on. Don't freak out. Don't even bother writing this down. You don't really need to, remember this or do this math, or you don't even totally have to fully understand it. But I did want to show it to you why that's the case. We started early in the semester when we were doing logs. We looked at this equation for sound intensity levels, and the equation was 10 times parentheses the square root of whatever your intensity level is, I over I naught, or our reference level. And that reference level, when we're dealing with intensity, is 10 to the negative 12 watts per meter squared. And that's the equation we started with to figure out intensity. So what if we want to figure out a change in intensity? Well, we can do that by taking this idea of the inverse square law and the idea of the area of a sphere, which is watts divided by, or the area of a sphere, which is 4 pi r squared, and watts divided by 4 pi r squared, and then watts divided by 4 pi r, 2 times pi r squared, which looks like this. And then if we take the initial one here minus the second one, we get the change. That's what the triangle is. Triangle delta is change in. And then we plug that into our equation, use some of our basic rules of logarithms. We can subtract these things out. I'm not going to go through the whole thing, so you don't need to totally understand it, because what really happens is by the time we use this basic idea of logarithms and subtract these things out, all of this interior stuff subtracts away from itself. You can pull those things out with some basic algebra, and we're left with 10 times the negative log of 4, and 10 times the negative log of 4 is negative 6.02 decibels, which is why all of that works. Pretty cool, right? So again, you don't have to totally understand that. I just wanted to show you why that's the case. Now, what we're going to talk about not is free field, but sound in an enclosure, and which basically is our boundary conditions for sound in a room. Okay, and so it does not act like free field because of the interactions with the boundaries and the reflections and the resonances that develop because of those boundary conditions. So just a little bit of review again, things we've already talked about when we looked at particularly a standing wave in a tube, is this idea of pressure, amplitude, and displacement. And standing waves have nodes and antinodes of pressure, amplitude, and displacement. And pressure amplitude, again, is the amount above or below atmospheric pressure due to that sound wave. And displacement is the distance that that air moves, create pressure variations, okay? And remember that the wall or the boundary condition of the tube, if it's closed, means that there can't be any displacement. Displacement has to be a 0. And the pressure amplitude is how that increases, because that air molecule can't move, right? Those two things are always 90 degrees out of phase from one another. Oh, this is what I kind of jumped the gun. But yeah, here, displacement is always a node at the wall, and pressure amplitude is always an antinode at the wall, because of what I just said. Now, also just a point here to point out, don't confuse mode and node, okay? A mode is a standing wave. We say a room mode, and when we say a room mode, we're talking about a standing wave. When we talk about a node is just a null or a 0 point where there's 0 net movement at that point, right? Just like when the guy could put his fingers on the string because there was no movement. It didn't affect how that wave was vibrating on the string. The same is true for a standing wave in a room, which is why there are places when we pipe that 50 hertz signal in a room that you could walk to and that sound just almost completely disappeared. It's the same idea. That is a node of the mode. Okay, hopefully that clears some of that up. Now, so there are several different types of room modes in standing waves, and the first of which that we'll talk about is called an axial mode. And an axial mode develops between two walls, any two walls, doesn't matter. But we'll say when it develops between the north wall and the south wall, that is one axial mode. When it develops between the east wall and the west wall, that's another axial mode. And when it develops between the ceiling and the floor, that's a different axial mode. So there are 3 axial modes for each room, okay? And then there are harmonics for each one of those 3 axial modes. N1, N2, N3 are the different harmonics, or the N integer number that we see up here. So this equation, F sub N sub 1, which is the first harmonic of this axial mode that we calculate by taking v, or velocity of the speed of sound in air, which is 1130, divided by 2 times the square root of n sub 1, and n sub 1 would be the fundamental, or that the first harmonic, which would just be 1, divided by L, the length of the room, say 10 feet, 12 feet, whatever, close parentheses squared. Okay, now I'm actually going to go through here and cut and take a picture and show you me doing this math for one example. I'm going to do this example for, say, just the axial mode of 10 feet. We'll say length is 10 feet. And so I write out my equation, F sub N sub 1 equals V divided by 2 times the square root of N sub 1 over L squared. Then I'm going to write in my 1130 divided by 2 because that's my speed of sound in air. I write 1 on the top because it's the first mode, or the fundamental, divided by 10, which is the length we're dealing with, squared. I'm going to crunch out the math, and that turns into 0.1 squared. Take the square root of, which is 0.01. I take the square root of that, it actually turns it back into 0.1. I do 1130 divided by 2, which is 565 times 0.1, which is 56.5. Then on the other side here, you can see I did F sub N sub 2, and basically did the whole thing, and then did 2 divided by 10, which turns out to be 0.2, and we end up with 113 hertz, which is the second fundamental, which is basically the same thing as doing 56.5 times 2. There is a reason for the more complex math, and that is if you're doing what comes next. Again, you're not going to do this math. There's much easier ways to do this. Fortunately, I want to show you how it works, but there are room calculators that I'm going to show you in a little bit to make this a lot simpler. But so we're going to look at the second mode that develops, and those are tangential modes. and they develop between four walls, any four walls. Think of a sound bouncing off of the north, then the west, then the south, then the east, and then back to the north, like the blue line there, or, whoops, excuse me, or this green line that bounces off of the ceiling, then the west, then the floor, then the east, and back to the ceiling, or the red, which is ceiling, then south, and then floor, and then north, and then ceiling. Those are all examples of tangential modes that develop between four walls, and they can develop differently than that. Those would be the four easy to visualize, and that equation is outlined by this be doing f n sub 1 and n sub 2, which is what, again, each one of these could have a potential n sub 1, n sub 1, n sub 2, n sub 2. It can get confusing. I think it'll make more sense when we look at the room mode calculator and the way that it lays everything out for us. And then here you can see a picture of how the intensity develops in the corners and along the walls, and a different way to visualize that with the red and the color schemes sometimes you see in modeling. Lastly, the third type of mode is called oblique modes, and oblique modes develop between six walls. And so the easy example is here, just going between north, south, east, and west, and ceiling and floor, in a simple to visualize pattern that looks like this, but actually they can bounce around in all sorts of weird and interesting ways that look something more like this purple line. And then here's sort of an attempt at a visualization of an oblique mode developing and the intensity levels with this cube here. And that's where we take into account length times width times height in our equation. We can actually crunch all these out numbers. Actually, when I took an acoustics class in school, there weren't as many of the online calculators, and I built in Excel a pretty comprehensive spreadsheet that laid all this out. It was pretty cool. Now, before I go show you a room mode calculator online, I want to just talk about optimum room sizes. And this is an example of, there's 3 A, B, and C optimal room sizes. But regardless of what the actual room sizes are, if you take this height, width, length proportions, and you say, we start with maybe what is most typical, which would be an 8-foot ceiling, and we call that 1, proportion 1. If we do 1.14 for a width and 1.39 for a length, and that would end up being 9.1 feet and 12.2 feet, then those are more optimal conditions because of the way that you space out the room modes, and you make them more even and less dramatic of overlapping peaks and nodes, so that you don't have as sporadic of jumps and spikes in standing waves. Again, the 8-foot is arbitrary. If we plugged in 10 foot here, you just do 10 times 1.14 and 10 times 1.39 to get the lengths if you have a 10-foot ceiling. And these create pretty optimum room sizes for having less problems and issues. And I'm going to stop here the PowerPoint for a second and go up here and go to bobgolds.com. You can just search Bob Gold. We've got all sorts of interesting resources. We might use a few of these later in the semester. I'm going to go to the room mode calculator. And actually, he's got a really clean, nice, neat dimension. This is pretty close to one of those that we just looked at, or another variation on an idealized room that has about a 7-foot ceiling, 11.4 feet wide and 12.4 feet long. And if we look at this, green is good, right? Most times in life, green is good. Green means go. And here it shows all of the modes that happen and each of the harmonics of each of the modes. So 1, 0, 0 means that if we went back and plugged in 1 into that big long equation that had all 3 of them, and 0 and 0 for, here, let me show you just to clear up. This one, 1, 0, 0, or 0, 1, 0, or 0, 0, 1. That's what these mean if you plug those numbers. Or n sub 2 would be for, if we were just looking at axial, would be 2, 0, 0. So this is the second harmonic of the axial mode is 90 hertz, which makes sense if the first harmonic, 1, 0, 0, is 45.3 hertz. And the third harmonic of the axial mode is 136 hertz. Okay? And so on and so forth. So that's what all of this stuff means. And you can see things are pretty evenly spaced, and there's not a lot of overlap, which gives us problem frequencies. Okay? If I go through and want to make a really, really bad room, the worst room that I could possibly make would probably be something along the lines of an 8-foot high ceiling that's 8 foot wide and 8 foot wide and 8 foot high, 8 foot long, 3/8. You get the idea. And which might be some of your bedrooms that you're trying to mix in. I don't know. And if I calculate that, ooh, you see how the greens have gone away? And what we have are, we have 70 hertz room mode for the axial, for the length, the width, and the height. And then we have this huge gap all the way up to 100 hertz. So there's frequencies aren't super supported here. And so they're going to be, these frequencies are going to be super strong, and anything in between is going to be really weak. And again, there's this big jump till we get to 120 and 140. And then look at all of these, how this happens to work with the second harmonic and the tangentials, how we've got all this buildup at 157. That would be a terrible frequency in that room. Same here, terrible 211 would be super strong and be really problematic in this room. And so this is just a calculator so you can see where your problems are, what you need to be mindful of. But let's just talk about this 8 foot for a second. 8 foot, most of you, if you mix in a house that has standard 8 foot ceilings, something that's just going to happen is at 4 feet, probably, which is pretty close to where your head is going to have a pretty solid dip at 70 hertz because of the node that happens at the halfway point between 8 feet. So that's something to be mindful of. Okay, let's go back to the PowerPoint here and play from current slide. And okay, so we talked about optimum room sizes. That's just a few more little concepts, and then we'll call it a day. Cutoff region is the frequency at which a room can't really sustain a sound well, okay? And it's below the lowest resonance of the room, meaning the sound isn't going to be able to fully develop and propagate in the room well. And it's smaller than half the wavelength in all dimensions, basically half of the longest dimension, okay? And so it's just going to be, again, that reduced ability to radiate sound and develop sound so the room can support it. And so basically that's F sub cutoff, or the cutoff frequency is velocity, which is 1130, divided by 2 times the longest dimension. So I'm just going to pull out a calculator here real quick and say, if you have a room that the longest dimension is 12 feet, which might be pretty common, and I'm going to do 1130 divided by, sorry, I'm not going to draw this up, but you're just going to have to play along at home, parentheses, 2 times, I'll do 12, because that's probably pretty common, close parentheses, equals, and the answer is 47 hertz. And that means if you're in a room where the longest dimension is 12 feet, that room is going to have a hard time really sustaining anything below 47. So even if you have a subwoofer, it's not going to be super efficient in that room because the wave can't fully develop. Hopefully that makes a little bit of sense. Now, actually, I'm going to jump this one. I think this one's kind of out of order a little bit, and talk about just these 2 terms. Modal region is the frequency range in which modal behavior dominates the acoustic performance of the room. This really common thing to keep in mind is that when you're dealing with small rooms, the problem that you have to counteract and be really, really mindful of most of the time is room modes. And you do that by looking at proportions like we just looked at, and have these hopefully evenly spread out modes if the proportions are laid out just right. And ideally, you want a larger room because smaller rooms are going to have more room mode problems and other issues. But modal is the modal problems dominate the acoustic performance of the room. And larger rooms, it's really, as you move into a large room, low frequencies can fully develop, and they're evenly spaced because frequencies can develop, and they have lower cutoff frequencies. And the problem becomes that it becomes too diffuse. And so the reverb time becomes more of an issue, and controlling reverb time with diffusion and absorption becomes the problem in larger rooms. But the diffuse field in a room is the frequency range in which the diffuse field can exist. So meaning, and the reverb time is valid, meaning that the reverb is even in the frequency range. And if we were to go back and look at that Bob Gold's, you have this nice evenly spaced out and supportive frequency ranges that reverb can be pretty flat in terms of its frequency response. And then basically, I'm just going to jump back here. There's this idea of this critical frequency in a room where there's that transition between modal behavior and diffuse behavior. That's called the Schroeder frequency. And that would be where, if you were to go back to that Bob Gold, where I kind of transition from and start to move into those greens, where I'm going to have an even balanced frequency response because of all of those three mode types: axial, oblique, tangential, are sustaining frequencies and room modes fairly evenly. Okay, I hope that makes sense. The good thing is this is a video, so you can go back and watch it 100 times if you need to. You can rewind, you can slow down and do some math. Try to do, I'd say try to do, measure out your room and try to calculate the basic, most problematic room modes in your room. And then pull up that Bob Gold's and see what that comes up with. See what if that correlates to, if you've done any room testing. We're going to talk about room testing pretty soon. Or if you're mixing, if you typically have problems at the frequencies that show up, like 70 hertz or 80 hertz, if you've noticed problems in that when you're mixing. So, okay, let me know if you have questions. Hope you're doing okay, and I'll talk to you soon. Bye.